Welcome back, everyone. Good afternoon. Before we start the panel, I want to introduce myself. My name is Kay Jowers. I'll be the moderator for today's session. I direct a program called Just Environments, a partnership between the Nicholas Institute for Energy, Environment, Sustainability and the Keenan Institute for Ethics. We focus on, as in the name, environmental justice and climate justice. And within our program, we run the Duke Environmental Justice Lab, which takes computational approaches and puts together teams of community co-researchers with students and faculty here at the university. So I'm very excited about today's panel and honored to be moderating. Thank you for having me here. Now, in terms of today's panel, we have 3 distinguished experts. They will each have 15 minutes to talk and share their insights and expertise. I want to call your attention to how you should submit questions so that I can see them and bring them up in our Q&A session. Please use the QR code and go to Slido to ask questions. And I'll be keeping an eye on time so that in that Q&A we can get through as many of your questions as possible. So now I'll make some brief introductions and then we'll get started. We'll start with Dr. Ben Rachunok. He has a PhD in industrial engineering from Purdue University and is currently an assistant professor at NC State. He was just telling me he grew up in Wilmington and his undergrad was at NC State, so welcome back to the Triangle. Ben's expertise is in developing statistical methods to quantify the impacts of climate change and natural hazards on communities. His work also puts a strong emphasis on researching distributional equity of resilience interventions by analyzing hazard impacts. And today, Ben will offer some valuable insights into the statistical aspects of climate impact assessment and resilience interventions. So without further ado, I am going to turn this over to Ben Rachunok.
Awesome, thank you, Kay. Well, thank you all so much for coming after lunch. I saw there was mac and cheese on the bar, and I said, everyone will be asleep. We're no good. Thank you. My name is Ben. I'm an assistant professor at North Carolina State University in the Department of Industrial and Systems Engineering. So a lot of our methods and a lot of the things that we do are very data science and very computational in nature. I apply this, and our research group applies this to the concept of we use AI and ML tools to think about adaptation to climate change very broadly. A little bit more specifically, we build statistical models, lots of times using AI and ML tools, to try to investigate or understand the impacts that a natural hazard, so you can imagine like a hurricane. I'm from Wilmington, I imagine hurricanes a lot. We can think about the way that a hurricane might impact a community, right? And the goal of all of our work is to try to have as fine a resolution about these impacts as possible, with the goal that this enables us to look at how cross-cutting ideas of social vulnerability impact natural hazard or infrastructure vulnerability. So at the end of the day, we're engineers and we're trying to populate or we're trying to provide information about who is going to be experiencing the impacts of natural hazards and climate change, right? That's the thing we're trying to come up with. The goal is then we do this with collaborators, putting this into decision-making models, right, to try to figure out what types of decisions we should be making to ameliorate any sort of these issues that show up. But this is generally the sort of flavor of what we do and the types of things that we work on. And I'll try to put a bit of a summary on the presentation that I'm going to give today, which is the benefit that I see in a lot of ways of these really nice artificial intelligence, machine learning tools that we use, is the idea of getting towards disaggregation, right? I can think about the impacts of a hurricane on, let's say, the power system by using a machine learning model to estimate if one individual household is going to be without power, rather than saying that Wake County or Durham County is going to have 75,000 people without power. So the idea of being able to disaggregate, right, being able to get to a very personalized, a very refined scale, then allows us to see who are these individuals that are being impacted, and we can try to dig deeper into the types of these impacts that we see. So when we talk about, I'm looking at the title of the session is Ethics and Social Responsibility of Data Analytics. Coming from the machine learning world, a lot of times we talk about this with the lens of interpretability, right? So fair and interpretable machine learning is a big buzzwordy topic in the sort of computer science world. And the idea is that I'm not just using my machine learning model to make some sort of an estimate and I'm walking away from it and washing my hands. I'm, one, digging into it to understand why is it making the predictions that it's making, but two, also understanding that it's making adequate or accurate predictions across different classes or across different populations. And so I have a really nice example of some previous work that is addressing a sort of socially relevant issue. It's using interpretability, and it really lets us dig into a lot of cool insights. But you all have to forgive me, it's in a water system, not an energy system. So please use your imagination. There's a lot of parallels. We're talking about residential water demand, so you can certainly imagine a lot of of ways that this applies to power. But for now, we're going to think about water because that's where we had access to the data. And this was in some collaboration with some colleagues at Stanford in the civil engineering department there. The social question that we're trying to address at the end of the day is water affordability in the state of California. So it's a wild statistic that over 1 million people in California lack access to some combination of clean, safe, and affordable drinking water. Right? That's a number that's higher than certainly I thought. As a result of this crisis, there was some empirical work that went out and measured water affordability and measured water quality. The California put into law this thing called the human right to water, which legislatively mandates that everybody have access to clean, safe, affordable water. There's no teeth to it, so there's no penalty if you don't have it. But it's meant to guide regulations. It's meant to guide California agencies towards trying to figure out how to make this better. This idea of the human right to water being violated, again, empirical work has done a very good job of identifying that this happens predominantly in historically disadvantaged communities. One element of this that we're certainly able to focus on is the concept of water affordability in California. So we'll walk towards the machine learning model and thinking about why we need this. Again, empirical work has sort of looked at water bills over time and has found that water bills are growing 2 to 3 times faster than inflation over the last decade. And again, we can think about this concept of water affordability, and if unaffordability happens only in people without means, right? This is generally happening in lower income populations or in lower income groups. The notional idea of water affordability, and I've written some papers trying to get towards this, we think about water affordability. Water is unaffordable if I'm spending too much of my income on it. So we can quantify or think about this as a ratio, right? Of the amount of money I'm spending on water divided by my total available income at any given time. What this means is that water affordability is then a function of my water bill and my income, where my bill is driven by the particular utility rate structure in which I live and my water use. So this is all walking us towards this idea that water use, water utilities, and the way that they structure bills and all of their rates, as well as my income, it's the 3 of these things together that ultimately lead to water affordability being good or being bad. And so to have an understanding or to move towards thinking about water affordability, we need to be able to quantify sort of the intersection of these 3 things, right? This is our goal. Very fortunate to have a partnership with the city of Santa Cruz in California. They gave us about a decade of their water bills, so we had access to about 10,000. Through this time period, there's about 10 or 15,000 households that have a consistent trace of their water use over time. So it was a very bad time for Santa Cruz because there was the big drought from about 2011 to 2016 in California. Santa Cruz was one of 3 municipalities that actually had to shut off water. Right? There was not enough water to go around. They have a reservoir that they use to store water, and they said if people continue to use water, taps are going to run dry, and we have to really heavily curtail our water use because there's not enough around. Very bad for the city of Santa Cruz in 2013. Very interesting is providing data for us to try to understand how these drought mechanisms contribute to affordability. We took a lot of literature, sort of summary literature. We developed a big comprehensive set of indicators that we thought at some point or another might contribute to household water use. So a lot of these are demographic in nature. We can imagine if you have a larger family, that's probably going to mean you're using more water. A lot of these are housing related. So if you have a bigger house, you have a big yard that you're trying to water, this is going to change your water use. There's certainly the utility component of this, that the utility rates and the utility rules regarding water use are a component of this. And of course, weather is also a big contributor of water use. So we take all this data, we gather all this data up, and the long and the short of it is we built a really good machine learning model. Our out-of-sample R-squared, the testing that we've done on this model to evaluate its quality was as good, if not better, than anything else that's on the market. And so we walked away from that. We sort of washed our hands, and it's the end of the talk. The goal of this, right? The goal of this is not to say that I'm able to estimate an individual household's water really well. The idea behind this predictive modeling paradigm, or the idea of using an AI or an ML model, is to say that I have now a really good representation of what's going on, right? My model now does a very good job of, to our sense of accuracy, representing what's going on in a household and what is contributing to water use. So then this is where the sort of ethical and interpretability part comes in. The goal is then we need to take this model and we want to bust it open, right? I want to see if this thing is actually representing what's going on. Let's dig into this, right? And let's use this good representation to try to understand more about what's driving water use, what's driving water use for different populations, what's driving water use for different groups. So here's a figure sort of showing some of our visual distribution of all of these after our example in the introduction about 4 different data sets that can all have the same mean and standard deviation. It's important, obviously, to take a peek at the distribution of all of our input data that we're thinking about. And I'm skipping methods. It gets way too lectury. Again, the mac and cheese, we won't do the methods on this. But so one of the first things we want to think about when it comes to some sort of a random forest model, this is a random forest model, our machine learning model, is we want to have a sense of what variables that I'm using are or aren't important. So if I'm doing linear regression, I'm using some sort of statistical significance for this, maybe a beta coefficient to assess the contribution of one variable versus another. In these AI models, we have to be a little bit more clever with the way that we do this. And the result of this, I'll sort of summarize this figure. These variables as they're listed, the larger bars indicate a greater contribution to our prediction. And we do this by taking them away, right? So if I run this model and I don't include temperature, my model gets a lot worse, right? But if I add temperature, it gets a lot better. So this is our notional idea of how much better these models are getting. Importance is something where you have a lot of definitions for. This is one of them that we've chosen. But again, if we're using this particular model as a way to try to assess what's actually going on in the city of Santa Cruz, this is telling us that all of these categories, the demographics, the physical housing, the utility policy, and the weather, all of these together are contributing to water use, right? All of these are showing up. Among the 40 or 50 things we tested, all of them can be considered important, again, depending on how you define importance. We can also go through and assess each marginal interaction between each variable that I'm interested in my response. So in each one of these figures, I'm taking the value of, let's say, temperature in the top left, and I'm moving temperature and I'm looking at changes in water use as a result of that. Again, to help build intuition, if you were using a linear regression model, all of these would be perfectly straight lines, and the slopes of them would be the beta coefficients coming out of your SPSS or your SAS software. But because we're using a nonlinear technique, we're using a sort of machine learning technique, we're able to see that there's a lot of nonlinear interactions between given values and my water use. And so this lets us see that temperature, for example, as temperature is increasing, generally speaking, water use is increasing. But if I look at a census block group level of renters, so this is in the top right, generally speaking, there's a sort of thresholding effect, right? And that water use is only changing for renters if we reach between 50 and 60% of the population. If they're 50 to 60% of a block group is listed as renting, then the water use changes, right? And we don't really see changes before or after that. So the goal of this, or what this allows us to do, is again to dig into what these relationships are and the nature of these relationships. And we can take this one step forward. Again, there's a lot of methods that sort of go into this. So we can take that same figure where I'm looking at the marginal impact of changing a value on the water use, and I can actually condition this on other characteristics in my data set. And this is where we really start to get at the concept of interactions. So again, if you're a linear regression person, if you're an OLS person, this is crossing variables in a very advanced way. But the idea is that I can look at how an individual change in a value of X, so let's say temperature again in the top left, I can see the impact of temperature on water use, and I can subset this, or I can condition this on other variables. So these red and these green lines in the top left are showing the marginal impact of temperature on water use for census block groups that have a high fraction of single-family homes, standalone homes, and a low fraction of single-family homes, multifamily, generally renters' houses. So what I can see from this is that the response of temperature on water use is heterogeneous across my population. That people that live in single-family homes have a high response to temperature on their water use. People that live in multifamily homes do not. Right, so this is allowing us to get further towards the idea of who is experiencing these types of impacts. If there's a drought, if there's a change in temperature, we're now able to dig into more specifically who is experiencing these types of responses. We don't see this for every variable. Some of these, like C, D, and E, so then the top right and then the bottom row, we generally see similar trends among these populations, right? But we're also able to identify, we did this for every combination of every variable, and these are the sort of 5 that were illustrative for this case study today. But the idea is that I'm able to use these AI tools, and I'm able to dig into them with the concept of interpretability to try to have a more fair, ethical understanding of what these predictions I'm making and what I'm able to draw as a result from this model. I'll put one more slide up here. This is some work that's going on right now that I'm going to be loose with my definition of what AI is, and we'll sort of call this data-enabled large computational tools. In my field, we call this like a simulation or just a big computational model. But we had this idea when we're thinking about the impact of natural hazards and sort of how it can propagate in different ways, that when people all of a sudden start to have electric vehicles, this is going to be a bit of a problem during power outages, like long-term power outages as a result of something like a hurricane, because your access is going to start to go away, right? Every time I drive my car, I don't have the ability to charge it if I assume that I'm charging at home. And this is going to limit my access over time. And the idea is that you are increasing the risk that you won't be able to get where you go every time I take a trip somewhere. So I have a grad student who's working on this right now where we essentially modeled this. We tried to look at the impact of technology and geography on these. And this is ongoing work, but we did a big computational exercise. We sort of modeled essentially every square mile of the US, and we looked at how close your nearest schools, hospitals, grocery stores, and sort of general political centers were, and imagining these are the things you might be interested in driving to during some kind of a natural disaster or some kind of a blackout. And we're able to assess how far, based on how far away you are, you're going to be able to take X number of trips to all of these locations. So we make some assumptions about where you're trying to go. But I actually can see, so after a few weeks, let's say it's a week of there being no power, I can look for every individual community and I can see who still has a lot of electric vehicle capacity to drive around and who doesn't have a lot of ability to drive around. And we quantify that here in Y as our percentage of residents who still have a sort of sufficient amount of capacity in their vehicles to move. And we can also measure through a thing called the Cohn-Pollock index. It's a Gini coefficient. You can think about it that way. We can measure a distributional element of how good is our best off and how bad is our worst off. And we can assess the inequity that's resulting in my communities. This is, again, sort of because of the way that these communities were built. But we see that, generally speaking, greater access is correlated or corresponds with places that have higher amounts of equity. So places that have a generally higher access to essential services in this idea that everybody has electric vehicles during blackouts. These are places that also have lower levels of inequity. And so as the access risk starts to go up, right, as your access goes down, generally we're seeing that this is correlated with places that have a higher level of inequity. We did some analysis that we're able to sort of correlate this with a lot of other variables. We find that this is generally the case in communities that are very car-centric. So high levels of car ownership, high levels of suburban sprawl, so low levels of density, are generally correlated with this risk, and so those places makes a lot of sense, those places have less access during these types of large blackouts. This is ongoing work. We're thinking about this in a lot of different ways. I'll put one more slide up here. We're also very curious about technology, so if I was interested in expanding the size of everybody's battery, this is going to only work in some places but not in others. And this is, generally speaking, a sort of empirical result due to the way that cities are built. If I have a community with a very dense urban core, then adding additional capacity doesn't really help. Similarly, if I have places that are very sprawly and rural, again, adding additional capacity doesn't really help. But there's very interesting classes of communities that are very suburban, by which adding a little bit of extra battery capacity really multiplies the access that people have. And it's very different across different population groups. We'll sort of leave it at that. And hopefully this can sort of spawn some questions on this idea of using these technological or these data-enabled models to evaluate the way that different people are experiencing these types of climate change or natural hazard impacts. And if you want to know the methods, send me an email and we can talk about it. Thank you.